Hello everyone, we are at the topic of diodes, and today we are going to look at waveform shaping circuits using diodes. There are four types of waveform shaping circuits based on diodes: rectifier, clipper, peak detector, and clamp circuits. These circuits are used to change the waveform of the input signals and generate a new signal at the output. Previously, you saw that we can represent the analog circuits with building blocks, where each one of these building blocks is a two-port network. One example of these two-port networks is a diode waveform shaping circuit. In this example, our two-port network consists of only one diode, and today in this lecture video, we're going to see how this network is going to affect the shape of the input signal. We would like to find the transfer function, or Vout versus Vi, in these circuits. After finding the transfer function or finding the relationship between Vout and Vi, we don't need to solve the circuit again for different RL values or for different given input signals. So we only need to solve this circuit in the two-port network once and find Vout over Vi. Then use that transfer function to find the output of this two-port network for different load values. Also, open loop transfer function is defined as Vout versus Vi when the load goes to infinity, RL goes to infinity. In other words, when there is no load connected to the output of the two-port network, or when Iout is equal to 0. The first diode waveform shaping circuit that we're going to study in this course is a rectifier circuit that consists of a diode. One terminal of the diode is connected to Vi and the other terminal is connected to our load resistor. I wrote the KVL equation for this circuit. I have this loop in here. I'm going to label voltage across the diode as Vd, and this is the direction of current flow in the diode, Id. And KVL tells me that Vi equals to Vd plus Vout. As a result, Vout is Vi minus Vd. Also, using Ohm's law, I know that Vout equals to Iout multiplied by RL, and I know that ID is the same as Iout. When the diode is off, using the piecewise linear model, I know that ID is equal to 0 and Vd is less than Vd naught. As a result, Vout is going to be equal to RL multiplied by ID, which is going to give me 0. So output voltage is 0. In addition, Vi equals to Vd plus Vout. Vout is 0. As a result, Vi equals to Vd. And I know that Vd is less than Vd naught. From there, I know that Vi must be less than Vd naught for this condition to be valid. So when Vi is less than Vd naught, Vout is going to be equal to 0. And let's move on for the case of the diode being on. If the diode is on, the voltage drop across the diode is equal to Vd naught and ID is greater than or equal to 0. From there, I know that Vout equals to Vi minus Vd naught. I found the relationship between input and output in this region. For this condition of the diode, I found this input-output relationship when the diode is on, and I would like to find the range of Vi for which this condition holds, and I can use this inequality. I'm going to say that ID equals to Vi minus Vd divided by R. Vd is equal to Vd naught, so I'm going to have Vi minus Vd naught divided by R. This quantity must be greater than or equal to 0. From there, Vi must be greater than or equal to Vd0. So I found this condition of Vi for the diode being on, and I found the output voltage. Let's see how we are going to use that to draw the transfer function. As you can see here, the transfer function is non-linear. When Vi is greater than Vd naught, or in this region, for these values of Vi on the graph, for these values of Vi, Vout is going to be equal to Vi minus Vd naught. So this is the equation of that line. and in this case the diode is on. For Vi values less than VD naught, the diode is off and Vout is going to be equal to 0. So this is the transfer function for this circuit. Now that I solved it, I can find the output for any given input signal without having to solve this circuit again. I have the transfer function and I'm going to use it to find the output for different input signals. Here is an example of using the transfer function to find the output of the two-port network for the given input signal. So Vi signal is a triangular wave. It's a time-varying signal. For different time points, I have different values for Vi, and different time points I have different Vi values, and I want to look at the transfer function to find Vout. So by looking at the transfer function, I know that when value of Vi is less than VD naught, the output is going to be equal to 0. In my graph for the given Vi, I can find the time points at which Vi is less than VD naught value. So let me draw a line for VD naught. Say that this is the line of VD naught volt. The amplitude of Vi is less than VD naught here, and also the amplitude of Vi is less than VD naught in this region. Also, it is less than VD naught in this region. Now, I can label the time points at which this happens. The value of the amplitude of Vi is less than VD naught at these time intervals, from here to here, from here to here, and from here to here, Vi is less than VD naught. So I know that for these time intervals, Vout is going to be equal to 0. In the bottom figure, let me find those time intervals. Again, this is the line for my VD naught, and whenever Vi is less than this VD naught value, Vout is going to be equal to 0. From there, in here, I have for this time interval, Vout is equal to 0. From this time point to this time point, Vout is equal to 0. And again, in this time point, Vout is equal to 0. So I'm plotting Vout of t as a function of t using red ink. I figured out the value of Vout for Vi less than VD naught for the time points at which Vi is less than VD naught. How about when the value of Vi is greater than VD naught? It is going to be this portion of the transfer function. I know the equation for this line. Vout is equal to Vi minus VD naught. So for these Vi values, Vout is equal to Vi but minus VD naught value. I can use this time point at which Vi reaches its maximum value, and I'm going to label it as V peak. So at this time point, Vi is at V peak. I know that Vi is greater than VD naught, and the value of Vout is going to be equal to V peak minus VD naught value. So I have 2 points of a line. I'm going to connect them together and get the line for my Vout. Again, for this portion, this is my Vout, which is Vi minus VD naught. At this time, in this time interval, Vout is equal to 0. Again, when Vi reaches its peak value, Vout also reaches its peak value, but the peak value of Vout is peak value of Vi minus VD naught. So I have this point of the line, and I can connect them together to draw the Vout signal. So in this example, we were able to use the transfer function and the given signal to draw the output voltage for the given input signal. This transfer function and the example input-output signals belong to the rectifier circuit. As you saw before, this is the diode RL. The output is taken from two ends of two terminals of the load resistor, and this is Vi. So the diode conducts only for the positive values of Vi greater than VD naught, and for those values Vout is equal to Vi minus VD naught. When the value of Vi is less than VD naught or negative value, Vout is going to be equal to 0. In other words, the diode rectifies the input signals, so when the input signal has a negative value, Vout is going to be equal to 0. If we flip the direction of the diode in a rectifier circuit, the way that I did in here, then we can keep only the negative portion of Vi at the output, and when Vi is greater than 0, or for positive values of Vi, make the output go to 0. So this happens because in the way that it is connected, the diode is connected in this circuit. The diode is going to conduct only for negative values of Vi that are more negative than negative VD0. So when Vi has a positive value, the diode is going to be reverse biased and it's not going to conduct. I can label the voltage across the diode as VD, and this is the current that flows through the diode. So when the diode is on, ID is greater than or equal to 0 and VD is equal to VD0. I can write KVL in this circuit, and KVL is going to tell me that Vi equals to negative VD minus RL times ID, the way that I label the direction of the diode current. From there, ID is equal to negative VD minus Vi divided by RL. Also, I know that VD is equal to VD0 when the diode is on, so it's going to be negative VD0 minus Vi divided by RL. This is going to be greater than or equal to 0. That's going to tell me Vi is less than or equal to negative VD0. So when Vi has a negative value that is more negative than negative VD0, then the diode is on, and just the KVL tells me that Vi out is Vi plus VD0. Also, when Vi is greater than negative VD0, the diode is going to be turned off, and the current is equal to 0. When the diode is off, ID equals to 0. And because the current is equal to 0, Vi out is equal to 0. Rectifiers are used in AC to DC converters for power supplies. The rectifier circuit that we just saw was a half-wave rectifier because it only rectifies half of the input signal, and we are losing the other half of the input waveform at the output. This problem can be solved using a full-wave rectifier, as you can see in this below picture. In a full-wave rectifier, all of the input AC waveform is going to be rectified to generate a DC value at the output. Let's see how it works. A full-wave rectifier consists of 4 diodes. Each pair of diodes conduct only for half of the cycle of Vi signal. So when Vi is positive, D1 and D3 are going to conduct, so the current is going to flow in this direction. It's going to flow through D1 and through RL and through D3, and here is the completing the loop. And when Vi has a negative value, the current is going to flow in this direction. D4 is on, D1 and D3 are off, and the current is going to flow in this direction. D2 is going to be forward biased, it's going to turn on, and the current is going to complete the path in this direction. So when Vi is positive, in order to turn D1 and D3 on, I need to have at least 2 times VD0 volts from my Vi to be able to make D1 and D3 forward biased. And when Vi goes above 2 times VD0 volts, the rest of the voltage is going to drop across RL. So when Vi is greater than 2 times VD0, VL is going to be equal to Vi minus 2 times VD0. As you can see in this figure, this is my Vi. When the value of Vi is greater than 2 times VD0, output is going to have a positive non-zero value, that the value of output is equal to Vi minus 2 times VD0. So 2 times VD0 volts is going to drop across the diodes, and the rest is going to drop across the R load. And when Vi has a negative value, and this negative value is less than negative 2 times VD0, because I need VD0 volts to turn on D4, and another VD0 point for turning on D2. So when Vi is more negative than negative 2 times VD0, then D2 and D4 are going to turn on. And for any Vi less than that value, the rest of the voltage is going to drop across RL. And VL is going to be a positive value. We can write a KVL in this circuit to show that V out has a positive value for negative Vi values at the input. So I'm going to label this one positive, negative VD, and this is positive and negative VD. For Vi values less than negative 2 times VD0, these diodes are on, and VD is going to be equal to VD0 for both of them, and ID is a positive value in this direction. ID has a positive value in this direction. So I'm going to write KVL here, and that is my loop. From there, negative Vi minus VD0 minus V out minus VD0. I finished the loop. It's equal to 0. From there, V out is equal to negative Vi minus 2 times VD0. So I know that Vi has a negative value for D2 and D4 to be on. Vi has a negative value, and this negative value is more negative than 2 times VD0. So I already know that Vi is less than or equal to 2 times VD0. As a result, this quantity is going to have a positive value. In summary, today we looked at rectifier circuits as a type of waveform shaping circuit. We looked at 2 types of half-wave rectifier and a full-wave rectifier. Thank you for watching.